So now we're going to look at other kinds of relations and determine whether they're symmetric, reflexive, or transitive. So this is going to entail a little bit more proof because it's talking about all real numbers, right? So we don't have like examples of numbers to choose from. Okay, so remember that the reflexive is every time I have an element in the set, so for any real number, for any x in the reals, is it true that x times x is going to be bigger than or equal to 0? Yes. If x is positive, it works. If x is negative, it works. So true. So yes, reflexive. Okay, let's check on symmetric. So that says for every x, y that I've got in the relation, right, that means y, x will be in the relation. So I got to think about this. So if x is related to y, that means x, y is bigger than or equal to 0. Well, we know by the multiplication rules that it doesn't matter the order. So that's going to be bigger than or equal to 0. So check. So yes, symmetric. Okay, so let's check transitive. So this says for all the xy's, I've got and the yz's in R, and so is xz in R, right? In the relation is xz. So if x is related to y, that means xy is bigger than or equal to 0. This means yz is bigger than or equal to 0. So let's think about this. Let's take some cases. So if I've got the case that x is bigger than 0, well then that must mean y is bigger than 0 also to be positive. Well, if y is bigger than 0, that must mean z is bigger than 0. And so then, or I should say bigger than or equal to, right? So that does mean that xz will be bigger than 0, bigger than or equal to 0 because they're all positive. What about their negative? So that's case 1. So what about case 2? What if x's and y's were both less than or equal to 0? Well, if y's are less than or equal to 0, that must mean z is less than or equal to 0. And so that gives us the fact that x, z, they're both negative, so that's less than or equal to 0. So check. Yes, transitive. Okay, so let me erase. We can go on to the next one. Another more proof kind of showing the properties. All right, so let's look at all the integers. Is this a reflexive? Okay, so reflexive means for every n in the integers, it does 2 divide n minus n. Yes, yes. 2 divides 0, right? So yes, it's reflexive. Okay, so let's go to symmetric. So for every mn in the relation, right, that means 2 divides m minus n. And the question we're asking is nm in the relation in R. And so that would mean 2 divides, 2 divides n minus m. Okay, so let's check it out. This translates to m minus n is equal to 2k. If I multiply here by a negative, so I'd get a negative m plus an n equal negative 2k. So that's m minus n, and then you just have to do a little configuring, right? So that this gives us 2l. So n minus m is 2l. So this does say that 2 divides n minus m. I got there. So yes, symmetric. Okay, so I'm going to do the transitive up here. So the transitive, so we have to have 2 elements that we're talking are in the relation. So transitive says, okay, if I have x, y in the relation, and I've got y, z in the relation, I should be saying the letter E, right? Because the relation's called E. Is it true that xz is in the E relation? Okay, so let's talk about I should not be doing x's and y's. Let me redo that. I should be doing m's and n's because we are in integers, right? So let me just write it. If 2 divides m minus n and 2 divides n minus p, is it true that 2 would divide m minus p? Okay, so let's go flesh this out. So m minus n equals 2k, and n minus p is equal to 2l. And I'm trying to get to this, right? So you can't use it. So let's just put these together. M minus n plus n minus p. That gives me 2k plus 2l. And look at that, the n's cancel. M minus p is equal to 2, k plus l. Yes, 2 divides m minus p, so transitive.